start. Okay, let's start today's lecture. Previous, in the last week, we learned what is eigenvalue and what is eigenvector, and I explained eigenvalue and eigenvectors for the notion of separate the vector space, a large vector space, to several small vector space. Like if you consider a vector space on and a linear operator on the vector space from V to V, then by restricting the domain, you want to see a large matrix as a direct sum of smaller matrices, W1 to WR, like here. So then we need to make this form of matrix. We will consider eigenvalue and eigenvector, and actually eventually we see eigenspaces. So we will make this space as a eigenspace. And actually, if the eigenspace is separated for each dimension, I mean if this divided as a one-dimensional block diagonal, 1, 1, 1, another is otherwise all 0, or lambda. We use the lambda as the notation of eigenvalues. So in this sense, to make this diagonal, to separate the into the smallest vector space, it is needed for dividing, for having each one-dimensional vectors, dividing to one-dimensional vector spaces. So in this case, it is very close to make diagonalize. Like if you have a matrix, matrix A, and we will say diagonal matrix is having entry on only the main diagonal entries, and another is 0, by choosing some by choosing a special basis. So, and I will explain why I write P inverse, and P is, when you consider a linear operator, we defined it. The problem of change of coordinate is that finding the matrix, like for gamma, here, the beta and gamma be basis for a vector space V, and let T be an operator, a linear operator over on V. Here, then by assigning a basis for V, we can represent it a matrix form, and coordinate change problem was that to finding this identity matrix, the coordinate change matrix, these two matrices, one is make coordinate change from gamma to beta is order 1 is mu1, and or beta to gamma is order 1 mu1. And we know that beta to gamma, coordinate change from beta to gamma is same to the matrix, the inverse of matrix gamma to beta. So I wrote this expression as this P inverse, and it is P. So the coordinate change matrix is saying we have an invertible matrix P to and its invertible matrix P will change the basis. So let me define one. Definition. Let A be an n times n matrix, and then we can consider one transformation maps A to P inverse A P. Here P is n by n square matrix, which is invertible. We can consider this transformation, and in which when we consider it, this map is called similarity transformation. Because we will say similar is if you choose another basis on the vector space, then you can represent it by choosing another basis. And so if you consider this notion to just a matrix, when A and B both are square matrix with same size, we say B is similar to A. So it is actually same mean to the transformation. It is making the all matrices to other matrices with other bases, and this is means there are some invertible matrix P such that E is equal to P inverse AP. Of course, it is okay to consider A is equal to P inverse BP. When this situation, we say that the two matrices B and A are similar. or B is similar to A. So when we consider this notion, we so far we have seen some invariance on a vector space, and actually this similarity transformation didn't have some invariancy. So these are called okay. So to understand the what property is invariant in the similarity transformation means what is the invariant property under changing of coordinates. It's almost same. So let's see some properties. Proposition. And I will use just A to P inverse AP be a similarity transformation. Then there are several properties. One is A and the image P inverse AP have the same determinant. Determinant was an important invariant on a matrix, and so the determinant gives the information invertible, whether by checking whether it is 0 or not. So invertible. A invertible means P inverse AP is invertible. And third one is A and P inverse AP have the same rank. Actually, if it has the same rank, then it will have same nullity as well. From the fundamental theorem of linear algebra, it is first property, and they also have same value of trace. Same trace. Trace was the sum of value of the main diagonal, and actually I want to mention this one. A and P inverse AP have the same characteristic polynomial. It means it will have same eigenvalue, have same eigenvalues, and also the characteristic polynomial is saying the dimension of eigenspace. Same dimension of eigenspace corresponding to our the same eigenvalues. So actually, by proving the sixth property, A and P inverse AP have the same characteristic polynomial, you can get another one, but I will prove the proposition 1 and having a trace and 6. Not 6. 4, 5 for nullity, trace, and characteristic. I think this technique very useful, and it will be used in another subject in math. So let me introduce it. Firstly, they have the same determinants, because when you see the determinant of P inverse AP, when we already seen the property of determinant, it can be divided 3 multiplication of like that, and we know that the determinant of P inverse is the inverse of the determinant of P. So actually it is same to determinant A. And so the similar matrix is have same determinant, and trace case also same. If you consider the trace of P inverse AP, when you consider it as a matrix multiplication of two matrices, one is P inverse, another is AP, then the trace is ij entry of P inverse multiplication ji entries of the matrix AP. And it is actually same the value AP ji P inverse ij. So it is the value of trace AP P inverse, and when you consider the if you calculate P inverse, it would be trace A. So trace value is also didn't change it under the transformation, similarity transformation. And finally, let's see the characteristic polynomial. It is also same. Characteristic polynomial was defined by the determinant P inverse AP. If you consider this matrix is characteristic polynomial, by subtracting lambda I and calculating the determinant, we get the characteristic polynomial, and we can consider it as identity matrix can be written P inverse multiplying P. So it is can be written P inverse lambda I P inverse. So by the distribute rule, it is same to A minus lambda I P, so that in the same sense it is same to A minus lambda I. So it was the characteristic polynomial of A. So it has same characteristic polynomial. Actually from this we can get another propositions as well. So I will skip the proofs. So now we'll see then how we can make a matrix to diagonalize. If you consider similar matrix, then by using the similarity transformation, you can find, if you choose an invertible matrix P, you can find any P. It will be similar, but if you want to find having this relation given A and given matrix is A and B, yeah. Yeah. Then you can choose any matrix P, any invertible matrix P. Yeah, like if you have matrix B and you want to find similar matrix A, then by calculating B, P inverse P given B and let P be invertible matrix, then if you consider this matrix or inverse BP is always similar to B because of the definition of similar. So if you want to find another similar matrices, you can choose any invertible matrix. But usually we want to aim a special matrices like diagonalized matrix or some other symmetric matrix. So in this sense, usually we ask that given a matrix B, given matrix is B, let me add the and by choosing a certain basis, you want to find certain form of matrix. Simple example, okay. Let's consider 2 by 2 matrix. Let be 1, 2, 2, 3. It is invertible matrix because the determinant is not 0. Actually, it is not important. And I will choose the invertible matrix P as 1, 1, 0, 1. It is invertible. Then if you find the inverse matrix of P, I'll use extended matrix form. Then by subtracting the second row to the first row, we can find the inverse matrix. So if you construct a matrix P inverse BP, it is P. I think it will be same matrix. Let's calculate it. 1 2 3 3 1 1 0 1. Then the first entry is 1 3 2 5 minus 1 and minus 2 2 5. If you define matrix A is minus 1 minus 2 2 5, then matrix A and B are similar because we can find an invertible matrix P. This is P. And actually, finally, we want to find some useful matrix from the given matrix B, like a diagonalized matrix or in some sense, useful matrices. To find the matrix, we need the notion of eigenvalue, and we will use eigenvector and its properties. So now I will construct the properties of diagonalization and eigenvalues, and then we should know what is diagonalization and what is diagonal algebra. Square matrix A is said to be diagonalizable means if it is similar to some diagonal matrix. That is, you can find an invertible matrix P like here, such that A P inverse AP is diagonal matrix. So finally, we want to get how we can get the diagonalized matrix here. So let's consider equivalent equivalent statement with diagonalizable. A is diagonalizable means A has n linearly independent eigenvectors. So by giving the proof, you can find what invertible matrix will make it as a diagonal form. Firstly, let's see the right side proof. Then we assume that A is diagonalizable. Then that means you can find an invertible matrix P such that P inverse AP be a diagonal matrix D. Diagonal. And equivalently, we can see the equation as the form of AP equal PD by multiplying P to left side or each term. And we will denote P as the column vector form P1, P2, and Pn. Then when you calculate A matrix multiplying P is okay. Okay. Yeah, it's okay. So if you calculate A matrix multiply P is AP1, AP2, and APN. And actually, if you calculate PD in this side, since D is diagonal, I will write it has diagonal vector, diagonal entries from lambda 1 to lambda n. It means the diagonal entries from lambda 1 to lambda n and other entries are all 0. So AP would be same to P D and diagonal matrix. If you calculate PD, then it would be same okay. I will confuse, so I will write the form on the end. Then the first column would be lambda 1 P1, and the second column will be lambda 2 P2, and so on, lambda n Pn. If two matrices are same, means APIs are all same to lambda IPI, and it means lambda I is an eigenvalue for A corresponding to the vector Pi. So it is the one way, and you consider from B to A. It is also same. The statement B was A has n linearly independent eigenvectors. Then you can, if you denote the independent vectors from P1, P2, Pn, then since n column vectors are all linearly independent, you can get an invertible matrix P from here. So you construct a matrix AP like this form, really it is same to the above form. It was AP1, AP2, AP, and which is invertible. And from the fact P1 to Pn were eigenvectors, then we can find eigenvalues corresponding to the vectors. Eigenvalues corresponding to Pi. So we can write it as lambda 1 P1, lambda 2 P2, lambda n Pn, and it means can be written by using a diagonal matrix D defining the diagonal matrix lambda 1 2 lambda n. Then we can divide. We can multiplying P inverse to the left side. We will get the diagonal matrix D. As the form P inverse AP. It means A is diagonalizable. So as you can see, to make diagonalized matrix, you should find n linearly independent eigenvectors. So today we will focus on the notion of linearly independent eigenvectors. First theorem is if you have k linearly independent eigenvector set, if you have different eigenvalues, it will give linearly independent eigenvectors. I mean, if the first proposition is lambda 1 to lambda k are distinct eigenvalues of a matrix A, and they are corresponding to Vi eigenvectors Vi. Then V1 to Vk is a linearly independent set. To check linearly independency, we used the form of linear combination, and since we choose firstly, to prove it, let's assume that V1 to Vk is a linearly dependent, then we can remove some vectors to make a linearly independent set. So firstly, we assume that it's linearly dependent. Then we can find a linearly independent subset. And I will denote it V1 to VR. Here R is the largest number to make linear independence, such that this set is V prime. V prime is linearly independent. Then from the assumption, since V1, if you gather all vectors from V1 to Vk, it should be a linearly dependent set. So that means R is bigger than 1 and smaller than K. Bigger or equal bigger than 0 and smaller than K. So if we want to VR is a linearly independent, then it will give a coefficient information when you construct a linear combination of them. I mean, if you construct a linear combination from C1 to CR VR equals 0, then C1 to CR all should be 0 because we defined it VR is linearly independent. And then by multiplying a matrix A, we already have matrix A. So by multiplying matrix A, it will give a linear combination of them. No. CR A VR. And actually, if you input one more vectors, plus C VR plus 1, then I will write the red one. CR plus 1, VR plus 1. Then we can find non-zero. Not all are 0. C1 to C R plus 1. Not all 0. Such that this equation. Then in the below equation, you will get this equation. And we defined it VI's were eigenvectors corresponding to lambda I. So this equation is same to C1 lambda 1 V1, C2 lambda 2 V2, CR lambda R VR plus CR plus 1 lambda R plus 1 VR equals 0. Oh, lambda R plus 1. Then we from this equation, we will get one more equation by multiplying just lambda plus 1. C lambda r plus 1 v1, C2 lambda r plus 1 v2, C r lambda r plus 1 vr plus C r plus 1 lambda r plus 1 vr plus 1 is also would be 0. And since we subtracting from this equation to this equation, you will get the equation C2 lambda 2 minus lambda r plus 1 v2 and so on. Lambda r minus lambda r plus 1 vr and equals 0. It will be cancelled. And in our assumption, lambda i's are distinct eigenvalues, so another vectors are not all 0. And since it is linearly v1 to vr is a linearly independent set, so that means c1 to cr all 0. It is from this we get the information that c r plus 1 lambda r plus 1 vr plus 1 is equal to 0 by star. And v and lambda is eigenvector and eigenvalue, so they are not 0. That means cr plus 1 would be 0. And it is contradiction to the fact that v1 to vr plus 1, v1 to vr plus 1 is linearly dependent. So, and we know that r could be until k minus 1, then that means we always should have k linearly independent vectors. Because if you have less than k linearly independent vectors, then by adding r plus 1, you can get a linearly independent set, larger linearly independent set. So if you bring k distinct eigenvalues, it will give k linearly independent eigenvectors. And the theorem, there is one more proposition, that is n times n matrix with n distinct eigenvalues is diagonalizable. We have seen that diagonalizable matrix means it has invertible matrix and linearly independent column. I will say again. Diagonalizable means there is an invertible matrix P, so it satisfied P inverse AP is a diagonal matrix, and it was then only if having A have n distinct eigenvectors. So if eigenvalues and eigenvalues are all different, then it will give all linearly independent and eigenvectors. Then the vectors would be may make the matrix A to diagonalized matrix D. So actually the proposition A is same proposition to B. Let's see an example making a diagonalized matrix. First example is finding a invertible matrix P which diagonalize the matrix A 0, 1, 1, 0, 2, 0, 2, 1, 3. In the previous section, we learned that to get the eigenvalues, firstly, let's calculate it. To calculate A, we will calculation what is the characteristic polynomial of A. It is minus lambda 0, minus 2, 1, 2 minus lambda 1, 1, 0, 0 minus lambda, and then it gave us 2 minus lambda 0 minus lambda minus 2 minus lambda minus 2. Then it is the square minus 5 lambda plus 6 minus 2 lambda plus 4, and so the characteristic polynomial is minus lambda cube plus 5 lambda square, and minus 6 minus 2 minus 8 lambda, and finally plus 4. And the eigenvalue was the solution of the characteristic equation, and if you input a lambda 1 to here, then minus 1 plus 5 minus 8 plus 4 is a little cheat. It would be 0, so lambda equal minus 1 is an eigenvalue of the matrix A. So it will divide the lambda minus 1, and if you divide it on the square, I will calculate it. Minus 5 lambda square plus 8 lambda minus 4. Not good at calculation. lambda minus 1, then lambda square, 4 lambda square plus 8 lambda minus 4, 4 lambda cube opposite the yep, if you if you calculate it, it would be then it is same to lambda minus 2 square.
There, or it's okay?
I wrote minus here, so I calculate minus this polynomial. So minus lambda cube, plus lambda cube minus 5 lambda square plus 8 lambda and minus 4. And if you calculate it, actually, let's calculate 8, then 4 lambda minus 4. So the dividing factors is lambda minus 2 square. So you can get the eigenvalues. One is lambda 1 is lambda 1 is 1 and lambda 2 is 2. So we will find actually lambda 3 is also 2 because lambda 2 have 2 vectors. Yep, right. So if the matrix A is diagonalizable, then this eigenvalue lambda 2 will be give 2 distinct eigenvalues. And if it gives just one eigenvalues, then we can say the matrix A is linearly not diagonalizable. No, not yet. We don't know it. Before calculate what is the eigenspace for corresponding to lambda 2. If lambda 2 have eigenspace of dimension 2, then it will give 2 linearly independent eigenvectors, right? And we said A have not distinct, linearly independent. Linearly independent means it span n-dimensional vector space. If n by n matrix have n distinct eigenvalues, then the matrix is diagonalizable. So actually it is not satisfied with the inverse way. The diagonalizer matrix can have same eigenvalues, but cannot have less than n linearly independent eigenvectors. Yeah. Yeah, right. Exactly. Yeah, right. In this case, we should check the eigenvectors, eigenspaces, because from this information, we can have two linearly independent eigenvectors. So we should find one more eigenvectors. So I will check it. Then it is obvious the eigenvector in corresponding to lambda 1 will be linearly independent with the eigenvectors in the eigenspace corresponding to lambda 2. So eigenspace was the null space. So I will calculate only lambda 2 case, and eigenspace was the null space of A minus lambda I. To calculate it, let's make augmented matrix 0, 1, 1, 0, 1. From here, actually each row vectors are all linearly dependent, so we can get the augmented matrix by calculating elementary row operations. Then from here it is the leading one, and another two vector is free term. So if you gather the vectors of this homogeneous equation, then it would be leading one term. If you give S and T, then leading one could be minus S from the first equation. And we are doing a real vector space. And ST is in here. So it means it spanned by two vectors, minus 1, 0, 1, and another is 0, 1, 0. Actually, if you calculate the matrix here by calculating multiplying the vectors, two vectors, it satisfies the equation. So we can find three linearly independent vectors, and first vector I will say V1, and it is V2, this is V3. I think it is better to calculate V1 as well. Let's show that. For the eigenvalue lambda equal 1 case, the null space could be given by the augmented matrix minus 1, 0, minus 2, 1, 1, 1, 1, 0, 2. Right? If you calculate it, 1, 0, 2, I will make row echelon form. 1, minus 1, 0, 0, 0. So you have two equations. That means you have only one free term, so that the null space of A minus I is spanned by free term T. If you input 1, then 1, minus 2, it will spanned by the vector minus 2, 1, 1. And let's define, this vector is v1. Then we found the 3 linearly independent eigenvectors, v1, v2, v3, and so the matrix A could be written if you calculate P inverse, here P is v1, v2, v3. I will write minus 2, 1, 1, and v2 was minus 1, 0, 1, and v3 was 0, 1, 0. Actually, if you calculate the determinant, then 1 minus 2 plus 1, so the determinant is not 0. Let's calculate it. Minus 2 plus 1 minus 1 plus 1, because here is the sign is minus 1. It is not 0. So P is invertible. By calculating the inverse matrix, you can calculate it would be the diagonal matrix, and the entries would be the eigenvalues. So lambda 1 was 1, lambda 2 was 2, and the v3 vector was also came from the eigenvalue lambda 2. So it could be the matrix form, diagonal matrix form. And let's see more examples. We calculate kind of general matrices, general 3 by 3 matrices. But if you see a diagonal matrix case, it's more easier to calculate it, because triangular matrices give us the eigenvalues as the entries of main diagonal entries. So if you see this example, let me give a non-diagonalizable matrix. So the following matrix is not diagonalizable. The given matrix A is 1, 1, minus 3, 0, 2, 5, 0, 0, 2. Actually, as we proved the previous theorem, the eigenvectors corresponding to 1 and eigenvector corresponding to the value 2 should be distinct, should give us two distinct linearly independent eigenvectors. And then we should find one more eigenvectors which is linearly independent to these two vectors. But if you calculate A minus 2 lambda null space, to calculate it, we should calculate the augmented matrix 1 minus 3, 0, 0, 5, 0, 0, 0. Then from the elementary row operation, you can get two linearly independent equations. I write here just one. And then you have only one free parameter, and that means it has the dimension of null space of a minus 2I is 1, because the free parameter, that there is only one free parameter. Calculate from here. I just divided 5 to the second row to make 1. It's okay to write just 5 because we need how many free parameters are there here. So we have only one dimensional eigenspace, so it cannot give two linearly independent eigenvectors. So that means the most number of linearly independent eigenvectors is just 2, and so the matrix is strictly smaller than 3. That means A is not diagonalizable. And then why we have these two distinct results? Actually, two matrices have same eigenvalues and same multiplicities for each eigenvalues, but it gives different results. I simply answer the fact. Let's consider the matrix identity 1, and another matrix is looks similar matrix J. If you calculate eigenspaces, I mean two matrices are all triangular matrices, so the eigenvalue of identity is 1, and it has 3 multiplicity. And in this case also, the information of eigenvalue is same, and the multiplicity is also 3, same to the identity matrix. But if you calculate the null space of one identity, then it's zero matrix. So the null space is 3. This is given by the homogeneous equation 0, 0, 0, and so the dimension is 3. It will be spanned by the solution set will be spanned by these 3 independent vectors. But in this case, the dimension of null space one I is, if you consider it, it will give the equation linear system over here. And if you see the matrix, then actually it will give the only one free term, two, not two. I will write like here. You have only one free parameter, and another is will not give the parameter, the free term. So that means it will expand by the vector 1, 0, 0, satisfying this equation, this linear system. That means the dimension of the null space is 1. So you can find the difference from the null space of the dimension of null space between the matrix I and J. So the J, it means the J matrix cannot be diagonalized. So in detail, we say the dimension of null space here. It looks important, so let's give a name. The dimension of null space will be called the geometric complexity. Not complexity, multiplicity. Of lambda is equal. Here is lambda equal 1, but now I will write more generally. The geometric multiplicity of lambda 0 is the dimension of the null space, that means eigenspace, dimension of the eigenspace corresponding to lambda 0. Lambda 0, and the algebraic multiplicity of lambda is equal to 0 is the number of how many vectors have multiplicity in the characteristic polynomial. So I mean the number of the vector lambda minus lambda 0 in the characteristic polynomial. Here, in previous example, we can see A's characteristic polynomial was lambda minus 1 and characteristic polynomial over A. was minus lambda minus 1, lambda minus 2 square. It was characteristic polynomial, and if you consider the lambda 2, it has 2 lambda minus 2. So it means the algebraic multiplicity is 2 of lambda equal 2. And we already seen that the nullity of a minus 2I has the dimension 1. I mean the dimension of eigenspace corresponding to eigenvalue 2 was 2. That means the geometric multiplicity of lambda 2 is 1. And the next theorem is saying, in this case also same, if I call this is geometric multiplicity is 3, and this characteristic polynomial I and j will have characteristic polynomial lambda minus 1 cube, and it means algebraic multiplicity is 3 of lambda 1. And here we get geometric multiplicity of lambda is equal to 1 is 1 because the dimension of eigenspace was 1. And then you can see that if the algebraic multiplicity has same number 2 geometric multiplicity, then it could be diagonalizable. And if it is different, then it could be it couldn't be diagonalizable. Let me write it as a theorem. So if A is a square matrix, then firstly, for every eigenvalue of A, the geometric multiplicity which was the dimension of eigenspace is less than or equal to the algebraic multiplicity. Because the algebraic multiplicity, the geometric multiplicity given from the homogeneous equation from here, it will be given the equation 1 minus 3 0 0 0 0 5 2 true. By calculating the null space from here, you will get the geometric multiplicity. But if you have different eigenvalue from the given eigenvalue 2, then this equation will give one equation. That means at least the dimension of null space should be less than equal to the number of the eigenvalue. This statement is saying that. And if A is diagonalizable, if and only if its characteristic polynomial can be expressed as a product of linear vector. It means if you calculate a characteristic polynomial, like here, consider the situation that you cannot find the linear vector, like assume that let's suppose that the characteristic polynomial of A was lambda square plus 1. In this case, if you consider the complex number, it can be divided lambda plus I, lambda minus I. But in real number sense, you cannot divide it like this way. So it is not linear form. And so this statement as a product of linear vector it can be vectorized to a linear vectors, and as I just said, the geometric multiplicity is same to the algebraic multiplicity. So we can consider the diagonalizability to think the multiplicity of geometric and algebraic. Okay, now it's time is very ambiguous to enter the next chapter. I just introduce what we will do next class. So in this sense, it is not pleasant situation because we want to make diagonal matrix. So, and actually, if you consider for the matrix A, whose have characteristic polynomial like this, and actually it has two different eigenvalues. One is minus I, and another is plus I. It has two different eigenvalues. Then it might give two linearly independent eigenvector in complex number over the complex number. So to remove this unpleasant situation, like having to reduce the statement of here, we will consider the algebraically closed field complex vector space. And actually, that is almost same to real vector space for the notion of dot product or linear combination or some even the form of n-tuple, because that complex vector space is actually we can consider as real vector space. Today I will give you the reason finally. Just some consider the complex n-tuple if n is a positive number, positive integer, then as we defined in real vector spaces, then a complex n-tuple is a sequence of n complex number. And we might write it as V1, V2 to Vn. And it is called the complex n space. The space whose gather these complex n tuples, the space of complex n tuples is called the complex n space. So as a remark, in n-dimensional complex space, the vector V will be written as the form V1, V2, Vn, and actually each Vi's are in complex number. Then we can write as a real number system A1 plus IB1, A2 plus IB2, B2, AN plus IBN. Then we, in real vector space sense, it can be divided the two form of A1, A2, AN plus I, B1, B2, Bn. Actually, we write this real part of V plus imaginary part of V, and it is very similar to the system of complex number over real number. Actually, it is same to the vector space of complex number. So if you consider just only the sequence, real of V, image of V is an element in R22N. So it actually have one-to-one corresponding from these equations. So the complex vector space is doubled dimensional real vector space. So any definitions of our complex number is very similar to the real number. But the difference from Yeah, we will do that next time. Actually, the difference comes from the just only conjugate, and another one is another is very same to real vector space.